More water. Water's good for you. Stay hydrated. Hydrated. As opposed to hydration, which we know from the video a couple of times ago there, like 3 or 4 videos ago. Hydration is the water surrounding, as a solvent surrounding the solute. So we remember that, don't we? Hydration. Hydrated. All right. This is going to be some theory. We have to go back to theory before we can do more problem solving. And if you have your list of stuff to go through, then we'll just dive right into it. First thing here is temperature effects. Okay, temperature effects on solubility. You know some of this stuff. Yes, you do. You know temperature effects and you know pressure effects. You do. You just might not know you do, but you do. And when I show you that you do, you're going to go, oh, I do. Okay. Okay. All right. Solid solubility. So what are the temperature effects on solid solubility? Our second lab coming up on colligative properties, we have to make hot solutions and we have to make cold solutions. You know this answer. I know you do. Does salt dissolve quicker, easier in hot water, cold water? Which one? You know, hot water. Much easier to dissolve things in warm water, dissolving solids anyways, in warm water than it is cold water. In fact, if we were together, you were going to do this lab on your own. I'm going to do it, so I'm going to have to suffer through it. But if you were doing it, you would find out that when we have those ice water baths, trying to dissolve salt in that is hard because cold water doesn't dissolve things very, very easily. So you know that's true. So you know when it comes to solids, that solids dissolve faster and more in hot water than cold water. So temperature effects, write it down like this. When it comes to solids, if you increase temperature, you increase solubility. This marker's dying. It squeaks. When when they're squeaking, they're dying. All right? So increased temperature increases solubility. You know that's true. You do. You know it's easier to get things to dissolve that the water is faster. And that's actually a reason why we have to talk about very soon reaction kinetics. That's actually I was going to say next week, but in the summer would have been next class. Our next class, we're talking about what are called reaction kinetics and something called collision theory. Not to go into it too much now because we will go into it in the next class, collision theory. But water is hot, and it's hot is because the particles are moving fast. I said water is hot. Water can be hot. When water is hot, the particles are moving very, very rapidly, and that means that they slam into things like salt particles faster. It gives them more energy and more collisions per unit of time that increases your ability to separate and dissolve. Okay? There's a little bit of theory behind that. We'll get into more theory when we talk about collision theory next class. Okay, so you know that. Okay, so what else we got next? Fractional, I'll talk about that in just a second. Fractional crystallization, gas solubility. Okay, gas solubility is the next thing on our list here. Well, actually, fractional crystallization. I'll talk about that right now. There are times, if we were together, we have more opportunities to do more labs. And one that I like to do, sometimes find it boring, but I like to do, is you take different salts, like potassium nitrate, sodium chloride, potassium chloride, mix them in water. Okay, heat that water up, and then let the water cool. So they're all dissolved. After a while, the water cools. You put it in an ice water bath. Water cools, 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 cools. You're taking temperature readings, and all of a sudden you'll see some white crystals reforming. The salts, 3 different salts in a solution, don't all crystallize at the same time. They crystallize at different temperatures. So if you want to separate a mixture of salt, then you have to do it by what's called fractional crystallization. Fractional meaning a part of the solution, crystallizing meaning solidify. So as you cool off your mixture of different salts, some will crystallize, form solids out of solution faster than others. And you do that by temperature differences. So fractional crystallization is a mixture a solution. Well, a solution is a mixture. It's a solution separation technique utilizing temperature effects of solubility. So what I just wanted to point this out though, so I guess what I want you to know out of this, that not everything dissolves equally at equal temperatures and not everything stays in solution as temperatures drop. They come out easier or more difficult than others. So, but you can use that to an advantage to separate mixtures of dissolved salts. All right? And if you know which one will dissolve first and what temperatures, and you, of course, you can go to a solubility table, you can see which crystallizing first, and you can go, that's potassium nitrate. And at a particular temperature, you can now pull that out. So it's a separation techniques for dissolved salts. That's what fractional crystallization is, utilizing cooler temperatures and solubility differences. Okay, gas solubility. Now, you know something about gas solubility. Yes, you do. Gases and temperature effects. So what are temperature effects on gases? You know the answer to this. You do. You go to your favorite grocery store or convenience, whatever, and you buy yourself a 2-liter container of your favorite soda, Coke, whatever. And, it's at room temperature, it's stored out at room temperature, right? You take it home, you got it at room temperature, and you open it, which is going to come into play very soon when it comes to solubility of gases. We'll talk about it just a minute. But you hear, okay, gas comes out. You'll see little bubbles come up, right? You've experienced this before. Of course you have. You take your drink, you pour it in the glass, put the top back on. What do you do with the soda? Do you leave it out? I mean, you might not have another drink of your soda for 2 days. Do you leave it out for 2 days? Or do you put it in the refrigerator? Most of us are going to put it in the refrigerator for 2 reasons. One, to get it cold. And 2, we know by experience, yes you do, that if you keep the soda cold, it'll stay carbonated longer. If you leave it out, it'll go flat quicker. Okay? You know that. If you don't know that, try an experiment. Take 2 1-liter containers of the same soda, open them up, just keep them open, keep the top off, and it'll happen quicker. Leave one out and put one in the refrigerator. Come back the next day, check them and see which one has some carbonation left. Not the one outside, the one in the refrigerator. Okay? Don't believe me, try it. So you know that when it comes to gases, that if you increase temperature, you decrease solubility of the gas. Okay? Increasing temperature means the gas doesn't stay soluble and it comes out of solution very rapidly. And that has to do, once again, has to do with what's called this collision theory. If you have high temperature soda, particles are moving around very rapidly, disintegrating your little gas bubbles, causing them to go away. If the cold, if you have it cold, your soda cold, particles in the soda particles aren't moving as fast, and they tend not to disintegrate your carbon dioxide so fast. So you know that. One other kind of little fun fact is when I was a kid, we used to go, there was this pond. Yeah, it was a pond, you call it a pond. Fishing hole, it was a pond. And we would go fishing there every once in a while, myself, my brother, and a couple of friends. We bring our fishing poles, ride our bikes there. And you were just catching carp. But some of the carp were really big. So we would catch these carp. I remember one day we went out there, and it was toward the end of a really long heat wave. It was really, really hot, like hot, in the 90s for days. And we went out to the fishing hole, and we got there, and all these fish, all the carp were dead. Well, what happened? That's what happened. Interesting little fun fact. The fish drowned. You ready? The fish drowned. The fish suffocated, they drowned. Fish can't drown, they swim in water, they breathe water. No, they don't breathe water. Fish breathe oxygen, just like you and I. They need oxygen to survive. Now the water is what goes over their gills. They have gills which take the oxygen out of the water as it's passing over their gills. Water, if they don't have oxygen in that water, they drown, just like you and I would. Okay, we can't get oxygen out of water, and if the fish don't have any oxygen in the water, they drown. So what happened was this. The temperature was so hot for so many days in a row that the temperature of that fishing hole got so warm that the dissolved oxygen content plummeted. The oxygen would come out of the water, come out of solution. So the water didn't have enough oxygen in it because it was too hot. Fish that have enough oxygen, they drown. No, sounds kind of weird, doesn't it? Yeah. Okay. Moving on. So you know something about gases. So when I'm talking about these solubility effects with temperatures, you know something about this. You do. I just have to point out that you know, but you don't. You know. What else do we have? Pressure effects on solubility. Okay, you know about this one too. We talked about earlier, just a few minutes ago, psst, psst, when you open up your soda. And then you open up, psst, and then what do you see? You see the gas, the carbon dioxide rushing up and going out into the atmosphere. So what are the pressure effects on gases? So this is pressure effects on solubility. Let's talk about gases. When it comes to pressure, okay, you know this answer. If you increase the pressure on a gas in a liquid, in solution, the pressure on gas in a solution will cause the gas to be blank soluble. More, which is why the carbon dioxide at the bottling plant for Coca-Cola, I'm advertising for Coca-Cola. I'm making money off this. Every time I say Coca-Cola, they give me $20. Yeah, Coca-Cola, 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 $100. All right, that's how I make my real money. Where was I? Oh, yeah, so at the bottling plant, they put the carbon dioxide under pressure, okay? David Bowie, Queen. Under pressure. Yeah, that's what they do. They put it under pressure to keep the carbon dioxide in the solution, because at a relatively warm temperature, you know, they're putting on shelves at room temperature, relatively warm, that gas wants to come out. It does not stay in there. The only way to keep it in there, tighten it up, put it under pressure, force the CO2 to stay in that solution. You take the top off, pressure gone, CO2 comes out. Pressure. If you increase pressure, now this is on gases, okay? We just did gases with temperature. Increase the pressure on a gas, and then literally, when you put pressure on a gas in a solution, the gas wants to get out, but you're the pressure. You say, no, you will stay in there. You will not come out, stay. You're forcing it to stay in solution. So increase the pressure, increase solubility. Okay. Well, what about pressure effects on solids or other liquids in solution? You have liquids in solution with liquids. I was talking earlier about alcohol. You could have alcohol mixed with water, putting pressure on it. That'll help, right? No, it doesn't do anything. When you're talking about liquids or solids, if you have salt water, and all of a sudden the atmospheric pressure were to triple, for whatever maybe reason, who knows? I just made that up. Maybe aliens make our pressure triple. That's not going to do anything. Or if our pressure, the atmospheric pressure goes from 1 atmosphere to half an atmosphere, that won't matter either. Pressure doesn't have any effect on gases, a major effect on gases, on liquids or solids in solution. Pressure has no effect, very little effect on liquids and solids, but big effect on gases. And you know this. You know pressure has an effect. Coca-Cola, soda. Okay, I got another $20. Said it again. All right, you'll see on the sheet that there is a law here. I put down here Henry's law. Henry's law, C is equal to K times P. C is equal to K times P. It's called Henry's law. Now, I'm not going to solve a problem with Henry's law. You know, we do the problem solving, and we're about to get into some more problem solving here very soon. But we're not going to do it with Henry's law. What I want you to know from Henry's law is about that concentration of dissolved gas is equal to, this K is a constant, depending on what the gas is. It could be CO2, it could be oxygen, it could be carbon monoxide, it could be nitrogen, whatever the gas is. There's going to be a different value for K for that. Here's what I want you to know. Concentration of your dissolved gas is directly related to pressure. They are directly related. In other words, if you double the pressure, you double the concentration of the gas dissolved in that liquid. Okay, they're directly related. That's Henry's law. Henry's law just says there's a direct relationship between putting pressure and how much gas you can get dissolved. If you triple the pressure, you'll triple the amount of gas you can dissolve in that solution. All right, so that will take us up to the point of colligative properties. Right here, colligative properties, and that is what the next 2 problems are all on. So we'll start the next video with defining what those are and doing some more problems. All right.